F being a number field, and we're going to let F ab denote its maximal abelian extension. And the first, theorem in explicit class field theory is the Kronecker-Weber theorem, which says that the field QAB, so the maximal abelian extension of Q, is obtained from Q by adjoining all the nth roots of unity for all positive integers n. So you could take a compositum or you could take a union. It's the same thing. So this is a famous theorem of Kronecker and Weber. So now what is the word explicit doing there? So class field theory kind of gives a partial generalization of this statement to arbitrary number fields F. So it explicitly describes the automorphism group, the Galois group of Fab over F, which you can view as an inverse limit of these finite groups, Fn over F, where Fn here denotes the narrow array class field associated to the conductor n. Okay. So the goal of explicit class field theory is to be more explicit, which is to not just tell us what the Galois group is, but to tell us what the field itself is, right? It carries more information. So you want to do this using analytic methods depending only on the ground field F. So somehow you want to, just starting from F, be able to construct all these abelian extensions F sub n. Okay. So an example is the Kronecker-Weber theorem. And so what do I mean by analytic and using just F? Well, if you just take the one function e to the 2 pi ix and you plug in the elements from the ground field Q, those rational numbers, then those give you the roots of unity that you need to adjoin to Q in order to get the maximal abelian extension QF. So this is the kind of the prototypical example that one wants to emulate for an arbitrary number field F. So let me give you the one other example, the one other case that's classically known where we can generate the maximal abelian extension of a number field. And that is when the number field in question is a quadratic imaginary field. So Q adjoin root negative D for D a positive integer. Then one of the fundamental famous theorems of complex multiplication is that the field that I denoted Fn before, the narrow array class field of conductor n, is obtained from F by obtaining first the J invariant of an elliptic curve with complex multiplication by the ring of integers of F. And so that gives you sort of F1 if you just take F adjoin J of E. And then to get Fn, you need to adjoin essentially the coordinates of the n torsion points on that same elliptic curve. Okay, there's a little modification having to do with the primes 2 and 3 that requires you to take what's called a Weber function of those points, but it's essentially just the coordinates of those n torsion points. Okay, so here the J function is the usual modular function, the Hupf module on SL2Z for SL2Z. So the point is, and so that's a modular function, and these coordinates of these n torsion points can also be viewed as modular functions applied to points in the upper half plane. And so you can rewrite this as taking F adjoin certain modular functions evaluated at the points in the field Q adjoin root negative D that live in the complex upper half plane. So it's very similar in nature to the previous example, the Kronecker-Weber theorem, where you took the analytic function e to the 2 pi ix. Now you're replacing that analytic function with these analytic functions, the modular functions, and you're plugging in, again, points from the ground field. So somehow you have these universal functions that are associated to the ground field, and then you have the points of the ground field, and you combine them just by evaluating the functions on the points, and you get elements that generate together collectively the maximal abelian extension of F. And that's kind of the goal of what one wants to do with explicit class field theory. And so Hilbert's 12th problem is sort of a codification of this question of explicit class field theory that he made during his famed ICM address in 1900. So I'm just taking some select excerpts from this talk, translated from the original German. So the theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. Okay, so this is just restating the Kronecker-Weber theorem. Since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So the time that Hilbert is speaking here, the theorem on complex multiplication that I mentioned already has not been proven. And so what Hilbert is saying, okay, Kronecker kind of know how to do this already, but you haven't finished it, so get going and wrap it up, please. All right, so that's what he's saying. Kronecker Kroneker's Jugendtraum was to finish this case. Actually, it's somewhat mistaken in the literature. Some people think that Kroneker's Jugendtraum was to solve Hilbert's 12th problem for general number fields, but in fact, his dream was not as ambitious. It was just to do the quadratic imaginary case. Okay, and so that eventually did get done in the literature. But Hilbert's 12th problem, what is it? Really is this. It's finally the extension of Kroneker's theorem to the case that in the place of the realm of rational numbers or of the imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. And since we have an entire conference week-long devoted to this problem, I'm sure we'll see a solution to this before the end of the week. All right, looking forward to seeing that. All right, so there's a link between Hilbert's 12th problem and the question of explicit class field theory. When I say explicit class field theory, I allow myself to be more general in what I might accept as a solution to that problem. Hilbert's problem, if you go in more depth in what he said than what I've written on the slides here, he was a little bit more particular. He wanted something very similar to the Kronecker-Weber theorem and to Kroneker's approach for quadratic imaginary fields, where he's looking for specific complex analytic functions using their with special transformation properties and looking at their special values to produce these number fields. So it's not particularly that precise because it's written, in sentences rather than in precise mathematical formulas. So what one accepts as a solution to Hilbert's 12th problem, I think, is a matter of subjective debate. But I think if one says more generally, we're looking for explicit class field theory, one can be more open-minded about what constitutes a solution to that problem. Okay. So now the focus of my talks with Mahesh is going to be the Brumer-Stark conjecture and certain refinements. And so what I want to do now is set up the conjecture and discuss its relationship to the motivation that I provided with Hilbert's 12th problem. So for this, we're going to restrict ourselves to a certain class of base fields, of ground fields, which I'll denote by F again. And I'm going to assume that they're all totally real. So we're only going to consider, number fields, all of whose embeddings into the complex numbers land into the real numbers. That's what a totally real field is. So for example, the prototypical example, the simplest example, other than Q, is Q adjoin root D, where D is a positive integer, positive non-square integer. Okay, and so we're going to take a finite abelian extension of this called H, and because of the method that we're going to be applying, namely through the Brumer-Stark conjecture, we're going to assume that H is a CM field. Okay, so and I'm going to write G as its Galois group, and then for technical reasons, we need two auxiliary sets of primes of the ground field F. We need S, which contains all the infinite places and the ramified places, and then we need another set called T, which is a set that's disjoint from the set S. Now, once we have all this data of our ground field, a Galois group, and sets S and T, then to each character chi of G, so I should have said what chi is here. Chi is a one-dimensional character of G, so it's just a homomorphism from G into C star. We can define the associated L function, which is given by the usual Euler product. You take 1 over 1 minus chi of p times nor of p to the minus s, but we only take the product over primes not in S, so that's how S plays a role. And then there's a smoothing factor due to Deligne and Ribbit. This is called the smoothing, where it's very similar to the Euler factor, except instead of nor of p to the minus s, you have nor of p to the 1 minus s. Right, and this is kind of a technicality. In some sense, we wish this wasn't here, but it allows for some very nice integrality properties of the L functions that will be very important for us to apply algebraic methods. Right. Oh, sorry.
Oh, these are all places of F?
Yes, thank you. Yeah, these are places of F. So the prime ideal, these P's are prime ideal, or the non-zero prime ideals of F.
And that's the ramified places or with
respect to H. Contains all the ramified, the places of F that ramify in H. So yeah, not absolutely ramified. Thank you. Yeah, so this could be empty, for example, if H is the Hilbert class field of F, this set of ramified places. All right. Thank you. All right, so let me just right away make the connection between explicit class field theory and Brumer-Stark units. So one can show, so Mahesh and I proved this in our I think this is probably well known, but we prove it as a lemma in one of our papers that if H is a cyclic CM extension in which P splits completely, then the Brumer-Stark unit U, which I haven't defined yet, but I will in a moment. For H, there's a certain unit in H called U. It can be shown to generate H, okay? And moreover, we show that if you take all the Brumer-Stark units, which I haven't, again, I should have probably defined it first, but I wanted to, as quickly as possible, make the connection to the implicit class field theory. So there's certain units that I'm going to define called U. And if you take all of them together and adjoin them to F, then you basically get the maximum abelian extension of F, except for the fact that the U's, I said, only generate these CM extensions. And so to get more general, extensions of more general signature, you need to throw in square roots of elements with arbitrary possible sign, and then that gives you all. So these are just alphas are just elements of F, so they're easy to write down, and then the U's are really correct elements. So if you somehow could prove the Brumer-Stark conjecture and then give an explicit formula for all of the U's, then you could say in some sense we've provided an explicit class field theory for F because we've written down explicit elements that generate the maximal abelian extension in the way that the Kronecker-Weber theorem gave us these roots of unity as generating the maximal abelian extension of Q. Okay, so now let me state the conjecture. So we fix a prime of F and a prime of H above it, which we call Gothic capital P. Okay, and all right, so the conjecture is that there exists a unit in the upstairs field, which is a P unit. So it's not actually a unit, but it has valuation supported at the primes above P, which I denote in this quick way. Say so. So I'm saying it has valuation 0 at all places that aren't above P, and it might have non-zero valuation at all the places above P. And it furthermore, so to compensate for the fact that it has non-trivial valuation at the primes above P, you actually get that it's absolute value 1 at all the Archimedean places, at all the complex embeddings of H. And now we're going to specify what its valuations are at the places above P. If you take those valuations, so all the places above P are the conjugates of this capital Gothic P. So I can write this as the ORD sub P of sigma of U, that's equivalent to ORD sub sigma inverse of P of U. So that's saying that if I take these valuations and take their linear combinations according to a character chi, then I get the special value of the L function that I defined before at S equals 0. So I should mention that Euler product that I wrote before converges to the real part of S greater than 1, but it extends via analytic continuation to all complex numbers. And so if we plug in, we're allowed to plug in S equals 0, and it's a theorem that not only is it non-infinite, it's a finite number, but it's actually an algebraic integer. Moreover, it's not just an algebraic integer; it can be written as a linear combination of integers with these roots of unity, these values of the character chi. So this is a plausible statement, and that's why we needed to introduce the set of primes T, because this would not be true without that set of primes T there. If T was empty, for example, on the right side, it would be a theorem of Klingon and Siegel that you get an algebraic number, but not necessarily an algebraic integer. So it would be a linear combination of chi inverse of sigma with rational numbers rather than integers. But of course, these valuations, these are integers. Okay, so for that to possibly be true, you need to have this be have the same form. And that's a theorem of Deligne and Ribbit, that if T is not only non-trivial, but satisfies certain conditions, which I won't give you, it's technical and not that important, but it will imply in particular that T is not empty, then this left side is an algebraic integer, so it has a chance of equaling the right side. So this should hold for all characters chi of G. And I should say that the number of sigmas is equal to the number of characters, right? The number of elements of a finite group is equal to the finite abelian group is equal to the number of characters. So you can solve those equations backward and get these valuations in terms of these L functions. So what that means is we've specified this use the valuations of it at all places, both finite and Archimedean. So we've said that is valuation equal to 0 at all places not above P. We've specified as valuations at places above P via this equation. And then we set this absolute value 1 at all Archimedean places. So we specified this absolute value at every place. All right, and that means by theorem of Kronecker that it's specified that it's unique up to multiplication by a root of unity. Now there's a final condition on this U, right? So the T has to play a role. If the T plays a role on the left side, it has to affect the right side. So the U does depend on the set capital T. And the condition that it satisfies is that U is congruent to 1 modulo all primes of H that live above T. Okay, and when you make that specification, the U becomes unique, not just under up to multiplication by a root of unity, but unique on the nose. And the reason for that is one of the corollaries of the assumptions on the set T that it didn't give you is that there are no non-trivial roots of unity congruent to 1 modulo T. So therefore, the U is unique. Any questions so far? All right, so let me give some pictures of some mathematicians associated to this conjecture. So Stickelberger, so this was all motivated by work of Stickelberger, actually in the late 1800s. So this goes back quite a while, when Stickelberger proved essentially, that this conjecture is true. That is, he found an element U that satisfied these properties, and really that's putting things in reverse. Stickelberger was interested in the elements U themselves. These are Gauss sums. And Stickelberger wanted to calculate the valuations of the Gauss sums. So he did that. He calculated the values of the Gauss sums. And then one can show, using the formula that Stickelberger proved, that this equation holds when the ground field F is Q and the extension H is a cyclotomic field. By Kronecker-Weber's theorem, we know that the abelian extensions of Q are all contained in Q adjoins zeta n for some n. So if you take, take a prime P and take Q join zeta n, then there's a certain Gauss sum that satisfies this property, and that's what Stickelberger proved. So in the 1960s, Brumer realized that Stickelberger's theorem should be generalizable to arbitrary totally real ground fields F, that one could make sense of these L functions, these L values that are non-zero. And by the way, I should mention that this is why we have to restrict ourselves to totally real ground fields. Those are the only fields for which those values L of chi 0 are non-zero. Okay, well, for which you can have non-zero values, otherwise just be getting something trivial. So in that context, Brumer, for totally real ground fields, essentially conjectured that units like this should exist. I guess one difference between the formulation that I gave and what Brumer had been considering was not having the set T involved. The set T is a little bit subtle and arose really, from work of John Tate. So Stark, meanwhile, had been producing conjectures about the existence of units, not P units like in our Brumer-Stark case, but actual units in abelian extensions of number fields, and had a series of beautiful papers throughout the 1970s on the existence of units whose logarithms of their absolute values are related to derivatives of L functions. And Tate realized that if you replace the Archimedean place in Stark's conjecture with the finite place, P, then what you recover is essentially Brumer's conjecture, except that there was some, imprecision in Brumer's conjecture that had to do with not introducing the set T. And so Tate realized that you can kind of introduce the set T and give a systematic, consistent presentation of Stark's conjecture with the Brumer-Stark conjecture, that when you specialize to a finite prime V, you recovered the Brumer-Stark conjecture, which he stated and called the Brumer-Stark conjecture for that reason. And if you replace it with, if you take V to be an Archimedean place, you recover Stark's conjecture. So you kind of unify this circle of ideas. Oops, sorry. So now I mentioned that, okay, so at this point you want to prove the existence of these units, okay? But before I had any ideas on how to prove the existence of the units, I was a grad student and had to write a PhD thesis. And so I did so at Berkeley, but I spent a lot of my time visiting Montreal and working with Henri Darmon. So I kind of have, if you look on Math Genealogy, I have two PhD advisors, Rivet and Darmon, even though they're separated by maybe 3,000 miles. my thesis, the goal of my thesis was to write down conjecturally, of course, because we have no idea how to prove the Brumer-Stark conjecture at this point, to write down a formula for the Brumer-Stark units, right? Conjectural formula. And this was inspired by Darmon's, at that point, recent breakthroughs on the construction of what he called Stark-Heegner points. Nowadays, people like to refer to them as Darmon points. And so by replacing the cusp forms that were appearing on Darmon's construction, in my thesis, replacing in that construction the cusp form with an Eisenstein series, I came up with a conjectural formula for the Brumer-Stark unit in the specific case where the ground field is a real quadratic field and the prime P is an inert prime from Q. So then was led to generalize this because the Brumer-Stark conjecture holds in more generality where you have a totally real field, the prime P shouldn't be forced to be inert in that field. And so this led to a sequence of very fruitful collaborations, and I have some of those collaborators here, Pierre Charlois, who's here, Matthew Greenberg, and Michael Spiess, in which we generalize that formula to the arbitrary setting. So at the conclusion of this sequence of collaborations, which took many years, we had a very general conjectural exact formula for the Brumer-Stark unit. So I said that the Brumer-Stark unit is specified uniquely by specifying its valuations, but of course that doesn't tell you what it is. If I tell you a P unit has, these are its valuations at the primes above P and has complex absolute value 1, now go find it, it's going to take you some work on a computer to eventually generate it. It's not like you just put that information and you can recover a polynomial that the unit satisfies, for example, right? What does it mean to write down an element in a number field anyways? That's a computational question. A reasonable answer would be you'll write down the coefficients of its minimal polynomial. So if you know its valuations, how do you go from that to the polynomial? It's hard to do. So that was the goal of my thesis, which then allows you to sort of access Hilbert's 12th problem or explicit class field theory, because you're not just proving these units exist, but you're writing down an exact formula for them. And then we have this theorem that they essentially, together with some simple square roots, they generate the maximum abelian extension. So if you can prove all these things, then you've made progress on explicit class field theory. Okay, so what is the form of the conjecture? So I'm not going to tell you the conjecture precisely because that would take an entire lecture, but just the what does it look like? So it's given by one of Darmon's p-adic multiplicative integrals. So there's a certain measure defined on so O here is the ring of integers of F, and I am assuming in this, just for the notational clarity, that the prime P is an inert prime, so say it's generated by a rational prime P, then OP is just the completion of OF at P, and OP star is its group of units. So this is a topological space, and you can write down a p-adic multiplicative integral, and it's just of the function x with respect to a measure that's defined on this space using what's called the Eisenstein cocycle. And there are some experts on the Eisenstein cocycle here whose names I've written out. Pierre Charlois and Luis Garcia have a new and exciting perspective on the Eisenstein cocycle, which we'll hear about. There's certain forms of the Eisenstein cocycle takes different manifestations. So this is kind of a p-adic incarnation of the Eisenstein cocycle. But this work on the Eisenstein cocycle goes back much further, goes back to Siegel, if I'm thinking that's right. Yeah, when he was integrating Eisenstein series on the upper half plane and writing down periods of Eisenstein series. And they know and the cocycle properties of this was then studied further by Glenn Stevens on studying so-called modular caps. David Solomon then realized that Shintani, this was kind of, I think, a conceptual breakthrough due to David Solomon. Solomon realized that Shintani's method could be fit into the Eisenstein, into the cocycle framework. And that led to a whole, new line of research. So Solomon had some joint work with Hu, and also that led to some of my work with both with Pierre Charlois and Matthew Greenberg, and also my work with Michael Spiess. there's a totally different approach due to Balance and Kings and Levin to understand this co-cycle. But anyways, so there's 10 different ways to think about this co-cycle. But at the end of the day, you get some co-cycle that's associated to a totally real field, and you integrate it, and you get the Brumer-Stark unit. Now, what is this zeta zero? This is very shorthand notation. This is basically some partial zeta function associated to the extension h. And so I'm not going to get into that, but this is something for which there are explicit formulas, mainly due to Shintani in terms of Bernoulli numbers, just like there are formulas for classical zeta function in terms of Bernoulli numbers. There are formulas for these kind of partial zeta functions associated to totally real fields in terms of Bernoulli numbers. Okay, so that's the conjecture. So this is explicitly computable. So I want to just do some examples. So for example, if you take q adjoint square root of 305, and the ring of integers is just generated by 1 plus root 305 over 2. And then for simplicity, we're going to take f to be what I would call f1 from my earlier slides, the narrow Hilbert class field. And we take p equals 3. Then you can write down this integral to however many p-adic digits your computer allows you. So maybe 50 p-adic digits, 100 p-adic digits. And you get some numbers that look like random numbers when you do that. But then you say, hey, if I do this for u and all of its conjugates, and then take all of this elementary symmetric functions, polynomials, excuse me, I should get integers or, algebraic integers in F, which are, elements of this ring. So you can do that, and you can ask, your program with Magma or what, I think they use Magma. I had some students code this, and you use Magma, and you say, okay, I have these random p-adic numbers, but they're supposed to live in this lattice, like in this, the Z lattice. What are they? And then you have crazy p-adic numbers that you can't understand at all, and then you ask it, and it gives you this small number that's like very exciting, right? That you've gotten something that looks right. So now that you have a reasonable candidate for what you think this polynomial, should be, you can then look at it more carefully and check that indeed this, splits over in a Galois extension of F, which is abelian. In fact, it's, it generates a Z mod 4Z, and that's what the class group here is. And you can check furthermore that this generates an unramified extension. The roots of this generate an unramified extension. So it is the right thing at the end of the day, computationally. So you can do this. So I did some computations like this in my thesis when I was trying to test my conjectures, but it's kind of done in a more refined way by some undergraduates at Duke. Okay. So here's a larger example. So he was 400 square root of 300, 473. The D here is just 473. And P equals 5, and you get the Z mod 6 example. And it's kind of amazing. You check at the end of the does this split over an unramified abelian extension of F, and it does. So we are really producing, and this is we call it explicit class field theory, because we're producing these integrals that generate these extensions. Okay,
Sorry.
so
Are there some example about cubic fields?
That's a really good question. So I had one student back when I was a postdoc in I'm gonna say 2005, 6, maybe 2008. He did one example in the cubic field, but it wasn't a super exciting example because the units were generated as Z mod 2 extension, like a quadratic extension, but it worked, right? He wrote down all the p-adic integrals and showed that it's satisfied. So there's one example. So, but yeah, it's not very robust. Whereas like in the quadratic case, we have like thousands of examples that have been computed. Like all D less than 1,000, I think they did it for a bunch of primes. But for cubic, I think it's pretty limited, the computations that have been done. It would be nice to get some more computations. Okay, so what are the theorems? So the theorem is, okay, the Brumer-Stark conjecture holds. So Mahesh and I proved this over Z bracket 1/2 first, and Mahesh is gonna spend 2 lectures covering the proof of that tomorrow and Wednesday. And then over Z, it was a lot more work. I would say the work to go from knowing the result over Z bracket 1/2 to removing that 1/2 and getting it over Z was more than getting the result over Z bracket 1/2. And Kyrie can say, like, they arrived at Duke when I had basically just done this and had no idea how to do this, and like every day I was like smashing my head against the wall trying to solve this problem. So that was exciting to finally get it. So and the second thing, which really comes from a breakthrough of Burns, Bullock, Dowd, and Seo, is that the equivariant Tamagawa number holds, which in particular implies that the conjectural exact formula for Brumer-Stark units holds. Okay, and so the implication to go, so it's a two-step, so I'll give a whole lecture on this at the end about the ETNC. It's a two-step process to go from the ETNC implies a conjecture of Gross called the Gross-Tower Fields conjecture. And then you have to prove that that conjecture implies our integral formula that I gave on the previous slide with Darmond's multiplicative integral. And so hopefully I'll be able to say where, both something about both of those implications. And I'll say that Mahesh and I proved that second, we would do this up to a root of unity, but Matthew Honor, who's also here, removed that ambiguity. And so we really get this conjectural exact formula on the nose. And now I've mentioned this already, but the Brumer-Stark units, together with those other square roots that I mentioned, generate FAB. So the two theorems together give an explicit class field theory for totally real fields. Okay, so yeah, I kind of already alluded to this. We obtained the equivariant Tamagawa number conjecture for the minus part of the Tate motive associated to H. And the idea to prove this comes from the work of Burns. So that'll be the time of my last lecture. Okay, so Catherine, are you happy? Yeah. Okay. So here's some sense of how we prove these results. Okay, so here's a picture of Ken Ribbett from the 1970s when he proved his converse to Herbrand's theorem. And it's really Ribbett's method that forms the foundation for our circle of ideas. So how do you relate zeta functions in class groups? Okay, so of course, the first answer to that question is just the class number formula. Class number formula at S equals 1 states that the residue of the zeta function is something in terms of a class group, class number times a regulator. But then if you start trying to make that correspondence between the zeta function and the class number more equivariant for the action of a Galois group, it suddenly becomes much more difficult. Right? That's really what Stark's conjecture is. It's an equivariant form of the class number formula. And somehow it goes from being something that's quote unquote easily proved using the geometry of numbers to something that we still to this day basically have no handle on. But Ribbett gives us a really good way to access this in certain cases, which is what the method I want to describe kind of qualitatively now, the circle of ideas. So Ribbett's observation is that these L functions or zeta functions that you're looking at show up as the constant terms of certain Eisenstein series. So Eisenstein series are certain modular forms. Okay, and their constant terms can be expressed in terms of L functions. Now, by taking linear combinations of products of these Eisenstein series, you can produce Cuss forms, right? That's actually how you produce the first Cuss form that you ever seen an example of, the delta function. You take E4 cubed and E6 squared, and now they both have weight 12. And you just you subtract, and you multiply one of them by a scalar to cancel out whatever their constant terms are. And then once you cancel out the constant terms, it's a Cuss form. That's how you make delta. Right, and so some generalization of that is Ribbett's idea of going from Eisenstein series to Cuss forms. But somehow the constant terms that I mentioned, that I kind of slid under the rug, you take, this linear combination to cancel the constant term. The fact that the constant term of one of these Eisenstein series is your L function means that the coefficients in that linear combination are going to involve that L function, and that's going to show up later when you're doing computations. That kind of, if you were to mod out by that L function, then one of the terms in this linear combination would vanish. Okay, now the reason that we want to go from Eisenstein series to Cuss forms is that Cuss forms have Galois representations associated to them that are irreducible, right? Irreducible Galois representations. So that's, comes from the work of Deligne and, initially over Q, but then in our context over totally real fields, there's a lot of work that goes into it due to, Carriol and Wiles and Hida and Taylor. So lots of people whose work goes into the construction of these Galois representations and the generality that we need. And then there's a very important step that produces from Galois representations that are reducible modulo some ideal to Galois cohomology classes. So when you produce your cusp form, as I said, the linear combinations involve the L function that you're interested in. That means modulo, say, the ideal generated by the L function, maybe your cusp form is just congruent to one of these Eisenstein series, which means that modulo that ideal, the Gauss representation, is reducible because the cusp form is congruent to an Eisenstein series. And when you have a Gauss representation that's generically irreducible, but modulo some ideal is reducible, then you can produce a Gauss cohomology class that sort of lives modulo that ideal. And that's Ribot's lemma. I'm going to say a lot about this during this week. So this is kind of in the algebraic part of this construction. There's a lot of work that goes into it. For example, there's a lot of beautiful work of Bellaiche and Chenevier. We just had a whole conference in Paris last week, memorializing the amazing work of Joao Bellaiche, who made breakthroughs in this field. And what Mahesh, Chuya, and Jesse and I had to do was to prove a new version of Ribot's lemma that applies in a case where you have an extension of two characters that are residually congruent. And so proving Ribot's lemma in that case was a pretty difficult project, was probably the most difficult aspect of finishing the proof of the Brumer-Stark conjecture. And then finally, the connection between Galois cohomology classes and class groups. Classically, this comes from Kummer theory. Right? This is kind of like the connection between Selmer groups and points on elliptic curves, right? The points on elliptic curve like sit inside the Selmer group, and the obstruction there is the Tate-Shafarevich group, and we don't know how to prove that that's finite in the elliptic curve case. In the units case, the version of the Tate-Shafarevich group that shows up is just the class group, and of course we know that's finite. So that gives a big advantage in the unit case over the elliptic curve case that allows us to make a strong link between Galois cohomology classes and the class groups. In the context that we're actually going to work, what's going to show up is certain modules called Ritter-Weiss modules, and we prove a Galois cohomological interpretation of these modules to give a concrete link between Galois cohomology classes and class groups. Okay, so that's kind of a preview of everything we're going to talk about this week. So first of all, what are the group rings that I mentioned? So you can package together all these L functions into what's called a Stickelberger element, which is an element of the integral group ring that has the property that's projection under each character chi is the L function in question. Okay, and so this is, I mentioned the role of this T, right? The T is what allows this theta to be integral, right? So the theorem of Klingen and Siegel is that there's a rational element, something in Q bracket G, that satisfies this, but the result of Deligne and Ribot is that it's actually in Z bracket G, right? I mean, for it to be even more weak and to say, oh, I want something in C bracket G, the complex number is C bracket G, well, that would be trivial because any numbers that you put here, they package together to give you an element in C bracket G that satisfy that. That's because C bracket G breaks up into a product indexed by the characters of copies of C. So any numbers in C that you put together, you get an element of C bracket G. The fact that you get something in Q bracket G is due to Klingen and Siegel, and the fact that it's in Z bracket G, Z for the integers, is due to Deligne, Ribot, and Cassou-Nogues. That's only if you include this set T. Okay, so now what is the class group? So I kind of, was talking about units, and then I started talking about class groups, but I didn't make the connection. I probably should have done that earlier. So the class group in question here will be the usual class group, except it's modified at T. So the usual class group is you take fractional ideals and you mod out by principal ideals. So that's what I'm doing, except I only want to mod out by principal ideals generated by elements that are congruent to 1 modulo T. And the Brumer-Stark conjecture essentially states that this theta annihilates the class group. And I probably should have explained this. So can I write on a board? If I write up here at the top, people will be able to see it. All right, so I write theta. People see this here?
Yeah. We can also change the setting, but if you're,
Change the setting, meaning like move this up.
yeah, I think. Is that what you want?
That would be good. That I think it'll be more people to see it easier. But I don't want to waste too much time because I have to
Yeah.
go back to the slides. I still have a bunch to do. So. Let's actually. Oh wow. Okay. Okay. So that was pretty fast. So hopefully we can. Okay. So I should have said this earlier in the slide, but so if you write your theta as sum of sigma times some integers, and the integers, these are the partial zeta functions that I wrote down earlier. I guess it would be sigma inverse, just the usual notation. So this is in Z bracket G. So these are integers, right? Because these are the ST partial zeta functions. Then if I take a prime ideal above P, right? So this is a prime ideal living above P. So here's H and here's F, right? Then if I take sort of the action of Z bracket G on this P, so you might write that this way.
Sorry, Samit, I don't know if you hear me. Speaking for the remote participants, all we see now is a nice view of a mountain lake. Thanks.
I'm sure that's more beautiful than my handwriting, but you know this, Henri. Yeah.
Okay, sorry. If it was intentional, there's no problem.
I'll be done in about 30 seconds. Okay, so it'll go back to the slide lecture in a moment. Then, all right. So what does this mean? This is just notation. This is just the product of theta of sigma inverse of 0, right? And so to say that it's annihilated in the class group, what's the trivial class in the class group? These are principal ideals generated by U's that are congruent to 1 modulo all the primes. Right? And that's exactly the property I want my Brumer-Stark unit to satisfy. But moreover, I can say that, oh, this unit has absolute, value 1 for all W not dividing P, because I can see, look at the factorization of the ideal that it generates. There's only primes above P in it. And furthermore, I can say that the valuation is I can just read off what the valuation is by seeing what power it shows up. That's zeta of, right? And then, so if I take the linear combination that I wanted, right, that's just then the sum of chi of sigma, zeta of sigma inverse 0. That's just L of chi inverse 0. Okay, and so that's exactly the what the Brumer-Stark conjecture was that there exists a unit which is absolute value 1 at all places not above P, and at places above P, this sum, this linear combination gives me the L function. Okay, so really saying that this theta annihilates the class group is okay. There's one thing that I cheated. I didn't tell you that it had absolute value 1 at all the complex places, which didn't satisfy this, but okay, so there's a subtlety at P equals 2. You have to replace U by U divided by its complex conjugate, which introduces a factor of 2, so you have to be a little bit careful there, but that's sort of maybe something I'll talk about more later. So hopefully we can.
I think if you press laptop,
Laptop, yeah.
it should go back to what it was.
Okay. All right, so now we've kind of replaced, trying to construct units, which is like a really hard thing to do, with something that seems more doable, which is to show that a particular element of a group ring annihilates a particular module for that group ring. Okay, but still, it's difficult, but it seems more plausible. Okay, so just some notation, this will be important coming up, which is that I'm going to define Z bracket G minus to be Z bracket G modulo the 1 plus C, where C is the complex conjugation. H is a CM field, so the Gauss group contains a unique complex conjugation. And so the minus part we defined by modding out by, it's the maximal quotient on which complex conjugation acts by -1. I just want to point out that I'm not inverting 2 here. So a lot of people maybe in this notation invert 2, but I don't want to do that. So this has sense even, at P equals 2, this is a nice integral thing. Okay, so what shows up is, or what turns out to be more important, or, is this Selmer group, okay? And so this was kind of, you know, a conceptual breakthrough for Mahesh and I when we learned of the work of Burns, Kurihara, and Sano, which is where we learned about the Selmer group. I mean, I guess they defined it. Were you guys the first ones to define it in this way this summer? Yeah. So this was, I think, a nice, I mean, you know, similar modules, I think, had shown up in the work of Popescu. But somehow we kind of put all these pieces together, reading all these papers, we kind of realized that the class group, the point is the class group isn't what shows up in the Gao representations associated to modular forms. What actually shows up is the Selmer group. So that was kind of important. And it's actually not the Selmer group, but a certain transpose we'll define in a moment. But this is the easiest thing to define. So this is kind of funny. You take HT squared. What is that? That's all the element of H star. So that just the multiplicative group of H. But you look at elements that have, you know, that are close to 1 modulo all the primes above T. So this kind of condition, U congruent to 1 modulo all the primes above T. So that's what I've written here. Okay, TH is all the primes above T and H. Instead of saying that mouthful every time, we just write T sub H. Okay, and it turns out you can show that this obviously has a G module structure. You just act on the H here. That gives you an action of G on the space of Homs. Okay, and I didn't mention, what is this Z mod or W? So the valuation at any place not in S or T, that is such a Hom, right? Just take the valuation at that prime, that finite prime. So if you mod out by all of those functions, then the functions that remain, that's called the Selmer group. And this is a very interesting module. So one thing is that it sees the units. So this is just Z-Hom. So just group homomorphisms from this free abelian Z module to Z, these are all G modules, by the way. Okay, and the class group. And the reason this is important is that I alluded to earlier to the class number formula, which says, you know, the residue at S equals 1 of the zeta function, other than some, you know, transcendental factors, is related to the class number times the regulator. It's kind of the most important two parts of that formula, the class number, the regulator. So what you want is something that's algebraic that sees that too, something that puts together the class group and the regulator. And so this is like a good sense that maybe the Selmer group is what you should be looking for, because there's a short exact sequence where on the left you have, okay, the Pointryagin dual of the class group, and on the right you have the units. This is like representing the regulator. So if you put them together in this is an algebraic manifestation of the zeta function, which is nice, because if you want to prove something related to the zeta function, maybe you won't see something that just gives you the class group. You'll see something that puts them together. So the zeta function, it's more natural to think that it would be related to the Selmer group. So that was like a very big, important insight that we gleaned from the work of others.
I'm sorry.
Yeah.
You told us what class group superscript T was? That's just the
Yes.
right class group?
Sorry, yeah, I don't think I told you. Yeah, thank you. I don't think I told you sub S. This means mod out by the image of the primes above S. So every prime above S has an image in the class group and mod out by that. And I also didn't tell you what this V meant. That's Pointryagin dual, so that's Homs into Q mod Z. Okay, this is a finite group. So as a group, Homs into Q mod Z is just isomorphic to it. But as a G module, it kind of alters the G module structure. So it's important to make that distinction. Yeah.
Is this some kind of dual of like a usual Selmer group? I'm used to thinking of
Yeah, like
class
some
number
cohomology.
class number being, or SHA as being on the right.
There's some interpretation of the Selmer group in terms of like Fey cohomology that I don't understand. I think you should ask Takamichi. Yeah. So there, yeah. So if you want to understand this in terms of étale cohomology or something, there is a way, but yeah. It's not so simple as just being étale cohomology, though. That's why it's a little bit complicated. Okay, so when I say you want to relate the Selmer group to a zeta function, and maybe it's natural to do so because you've put together the units in the class group, okay, how do you relate them? Well, it's the theory of fitting ideals that allows you to relate, you know, this algebraic module to a certain element of a group ring, which is this theta. Okay, and so let me define fitting ideals, because maybe not everyone has worked with them, even though it was, you know, really brought into algebraic number theory, at least from the literature that I've read, by the work of Mazur and Wiles on the classifier. Would you say that's correct? Tate brought in. Okay. Yeah. So, but it played a big role in the proof of the main conjecture by Mazur and Wiles. But yeah, okay. So what is a fitting ideal? So let's say you have a finely presented R module. In fact, I was thinking the other day, I don't think you really need it to be finely presented. Just finely generated is probably good enough. And you want to define the fitting ideal. It's the maximal zero fitting ideal, which is the ideal generated by all m by n minors of the matrix representing this map. That is, if you have some map here, it's represented by an m by n matrix. And if you take, m is the number of generators, and you take all sort of square submatrices, maximal minors of this matrix that you can take, then you get what's called the fitting ideal. If n is equal to n, then the terminology is that m is quadratically presented, so n equals m, and then it's just the determinant of that one matrix. The determinant of the map. That's principal in that case. So here are some properties of fitting ideals, if you've never seen them before, that are very important. So the fitting ideal of R mod I is just I. So that's really easy. Let's see why that's true. R mod I is generated as an R module by one element, namely the number 1. And what are all the relations? They're all the elements of I. Those are all the things that are 0 in the quotient. So we're looking at the 1 by 1 minors generated by the elements of I, namely I. So you just get I. Okay, so that's simple. So this is a very nice exercise that the fitting ideal is contained in the annihilator. Okay, and so that's actually how we access annihilators. I said I wanted to prove that the Stickelberger element theta annihilates the class group. You actually end up proving something stronger in terms of fitting ideals. So theta is actually in a certain fitting ideal that implies that it's an annihilator. Okay. So just to be clear, I'm not saying that theta is in the fitting ideal of the class group. That turns out to not necessarily be true, as was discovered by Christian. But it's essentially in the fitting ideal of the point-dragon dual of the class group, which is good enough. But how should you think about fitting ideals in comparison to annihilators? I think a really good example is the case of finally generated Z modules. So let's say I have a finally generated Z module, then you can show that if the Z module is infinite, then the fitting ideal is 0. Okay, well, let's look at that finite case. That's interesting. So we have a finite abelian group. So what's the annihilator? That's the exponent, right, of the group. So if I have a product of Z mod DIs, it's the LCM of the DIs, right? But what's the fitting ideal? The fitting ideal is generated by the product of the DIs, right? The size of the group, right? And of course, the LCM of the DIs divides the product of the DIs, so you get this containment. You see it easily in that case. But so a way of thinking about the fitting ideal is it's a notion of the size of a module. It's the way of thinking about fitting ideals. So particularly how big the module is, but it has more refined information. It's not just a number. It's an ideal of the ring. So in the group ring, you get an element of Z bracket G. Okay, so two other properties that I'll state. If you have a surjection of modules, then you get an inclusion of fitting ideals. That's a really important property that you can check easily from the definitions. And this is probably the most important property that makes fitting ideals better and easier to work with than annihilators, is that they behave well with respect to base change. If you tensor with another ring, then the fitting ideal just extends. So this is very much not true for annihilators, for example, right? You can never hope to prove something like this. Okay, I'm gonna start a few minutes late, right? So I can go a little bit over. Okay, they just said I'm almost done. Okay, so this was the conjecture of Burns, Kurihara, and Sano, which is that the fitting ideal, the Summer group that I gave you, is generated by theta. And just to be safe, I projected onto the minus side. Maybe this is true even without projecting on the minus side. This is the concrete statement in the group ring, context of saying that this Selmer group is the avatar of the L function. So these theta is the group ring version of what you get when you put all the L functions together. So this is like our zeta function, if you will. And I said the Selmer group should be the algebraic manifestation of that because it sees the class group and the units, right? And so what is the precise statement that links the two? It's this statement that the fitting ideal of the Selmer group should be theta. And one can prove from this statement that the theta, the Stickelberg element, does annihilate the class group. In fact, you get an improvement by a factor of 2 to the n minus 1, where n is the degree of the extension f over q. Okay, and so that this being able to divide by power of 2 allows you to get rid of the issues at 2 that I had alluded to earlier, that where you need to replace in the statement of the annihilator u by u divided by its conjugate in order to really get the absolute value to be 1 at all the complex places. You have this extra power of 2 helping you. All right, so you can prove that this implies Brumer star. Okay, so this is really what it is that we're going to be proving over in the course of the week. So this holds even at p equals 2. Okay, so I'm just going to end, because what actually turns out to show up in the Gauss representations is not the Selmer group itself. The Selmer group was easy to define just in one line as the quotient of this, Hams of HT star into Z by some subgroup. What shows up is a certain transpose of the Selmer group that due to Ritter and Weiss. So what is a transpose? So if you have a finally presented module, okay, then you can define what's called the transpose, which is you just take the Hams of these into R as R modules. So this is, of course, isomorphic to R to the M as an R module. It's just, right, Hams. If you take row vectors, you get column vectors or something. But so this map has a, when you Ham it, the map goes in the other direction, right? So Hamming is contravariant. So you get a map from Hams from R to the M to Hams to R to the N. And the reason it's called transpose is because if you have a matrix for this map, then the matrix for this map is just the transpose, right? So if you take the co-kernel of this map, that's defined to be the transpose of the module M. Okay, and so one thing I should mention is that this depends on the presentation that you take up to what's, I think, called projective equivalence. It's like if you have two modules and you can add projective modules to each to get them to be isomorphic, they're called projectively equivalent. So this M transpose is not uniquely defined. It depends on the presentation you choose. But there's a certain canonical presentation you can take of our cell, and the transpose of that of cell with respect to that presentation is called the Ritter-Weiss module Nabla sub ST. And maybe, I'm not sure if Maj will define it precisely, but in his talk. But what's really important is the kind of version of the short exact sequence I gave before, where we had the class group dual and the Hams of the units into Z, the version of that for Nabla. So where you have a submodule, which is the class group, not its Pointryagin dual anymore. And the quotient is actually a much simpler module than the units. It's the thing that usually goes along with the units when you define the regulator map, which is just the group of degree 0 divisors on the place above S. Okay. So I'm just going to end with this slide. So the conjecture that I mentioned earlier, Burns, Kurihara, and Sano, which we prove, in which Christian has another version of the proof of, can be stated in terms of the Nabla, because it's easy to see from the definition of the transpose that that Selmer and its transpose have the same fitting ideal, because in this case it's quadratically presented, so the matrix is just a square matrix. So I'm just saying that a matrix and its transpose have the same determinant, right? So it's a very simple statement. Okay, so this is a principal ideal generated by one determinant, and I'm just taking as transpose, so it has the same determinant. So it's equivalent to say the fitting ideal of Nabla is generated by theta, and that's really what we prove, because this is the module that kind of shows up in Gauss representations, as we'll see when we talk about modular forms of Gauss representations. And then a very important observation, and this is what I'll end with, is that in order to prove this equality, it suffices to prove an inclusion. Okay, and so that's actually what we prove using Ribot's method. Okay, the circle of ideas that I gave before. At the end of the day, we're going to get an inclusion of the fitting ideal into theta. And the thing that's interesting about this inclusion is that it's the reverse inclusion from what you want at the end of the day. What you want at the end of the day is that theta is contained in the fitting ideal of something, right? Theta is contained in the fitting ideal of the dual of the class group or something like that. And what you're proving is that the fitting ideal of Nabla is contained in the ideal generated by theta. Okay, and the reason that that's good enough is somehow this inclusion implies an equality, which then implies the other inclusion. And that's why it was very important for us to have a module whose fitting ideal actually was equal to theta. When we were sitting there looking at the class group, it was very difficult because we could only do it in the cases where, secretly what was going on, which is that the class group was equal to Nabla. And so you know, and so the inclusion in the wrong direction was giving us the inclusion in the right direction. But unless you have the module whose fitting ideal is supposed to be equal to theta, then proving an inclusion in the wrong direction doesn't give you the inclusion in the direction you want unless they're actually equal. So it was kind of very important. I remember very clearly this trip that I made to London, and Takamichi was visiting David. It's a very nice coincidence, and so we went into his office, and he kind of explained to us that, okay, you have to use this Selmer group. So, all right. So I'm gonna end there, and Mahesh will take over. I think that's my last slide. Oh, sorry. I have one more slide, one more thing to say. I should say that there's a cohomological interpretation of Nabla, and hopefully we'll see more details of this in the upcoming lecture, which is that there's a functor that Nabla represents a functor. It represents a functor that takes a module and spits out cohomology classes valued in that module. Okay, so to give a surjection from Nabla to a module is equivalent to producing a cohomology class, right? And so this is the reason that I wanted to end with this slide, because I gave you Ribot's method, and the whole end of the circle ideas was I produced a cohomology class. And that's how that ties this together. Once you have that cohomology class, you have a surjection from Nabla to something that can tell you something about the fitting ideal. Remember I said if you have a surjection, you get an inclusion of fitting ideals. So that tells us something about the fitting ideal of Nabla, which then tells you about something about annihilators, and that gives you Brumer story. All right. So I'll end with that. Mahesh will take over tomorrow.